what we're going to do now is look at equality constrained minimization, and we're stepping slowly towards solving general convex optimization problems, right? so, so we're going to add constraints, but the easiest constraints to handle are equality constraints, which are linear. Okay, and it's going to turn out actually, there's a few interesting things here, but some of it is actually, it turns out to be quite simple. We just reduce it to the other one. Okay, so we want to minimize f. F is smooth, subject to ax equals b. And we're going to assume that A is full rank. It's wide and full rank. And we'll assume the optimum is attained, right? And so basically it says you simply want, these are the necessary and sufficient optimality conditions, right? It's the KKT conditions. Nu star is an optimal dual variable here. That's the, or Lagrange multiplier. And so you want to solve these two equations. And let's stare at the two equations for a minute. Interestingly, these equations are affine in nu star, right? They're not nonlinear in nu star, they're affine. Now, what are they in X? Well, that's linear, right? It depends on that. Oh, except for one case. When is the gradient of a function an affine function? When it's quadratic, right? So if the function is quadratic, these are a set of linear equations, okay? And that says that solving linearly constrained quadratic optimization problems is pure linear algebra, right? That's it. You just set up linear algebra and you do it and you solve it, okay? So, but in general, this thing, if f is non-quadratic, this is non-affine, and that's a set of nonlinear equations. By the way, people have names for the residuals, right? The name for the residual in this equation is called the primal residual, and sometimes denoted Rp. And the condition, of course, the optimality condition is Rp equals 0. This one, that expression on the left is called the dual residual, and it's denoted Rd. And of course, the optimality condition is that Rd equals 0. So you're looking to find x and nu that make Rp and Rd 0. Okay. And by the way, the number of equations is about right. You have m plus p variables, right? N plus p variables, and you have n plus p equations. So, but they're possibly nonlinear. Okay. So, well, we already talked about this, right? If you want to do equality constrained quadratic minimization, it's linear algebra, and so you get something like this, right? You write the optimality conditions this way, and you're actually computing both x star and nu star, which is an optimal Lagrange multiplier. You compute both of them. By the way, there's some structure here. There's a block of zeros, and your eye should be looking at it or something already without my saying. I mean, there's not a lot. You can have more structure, but that's that. And it turns out, I mean, you can work out a lot about this KKT matrix. For example, it's non-singular if and only if you're in the null space of A, P is positive definite or something like that. So another way to say that roughly is P is positive definite on the null space of A, right? So P has to have positive curvature kind of on the feasible set. That's the right way to say it, okay? That wasn't quite right, but that's the spirit. Okay, so that's a set of linear equations. There's a very general method for handling equality constraints. Is you just eliminate them, right? So you would do the following. This is my constrained representation of an affine set, but I will write it instead as a free parameter representation. And so what I'll do is you compute an x hat that satisfies ax equals b. That's this one. Lots of names for this. By the way, a traditional name for this is x sub p for a particular solution. That's the 19th century name. Is you have a particular solution. I think the other one's like a homogeneous. I don't know. Anyway, so that's a particular solution. Sorry, and then F is a matrix whose range is exactly the null space of A. Right? Lots of ways to compute that. That's just linear algebra. Right? So tons of ways to do this. You use a QR factorization, all sorts of things, all sorts of ways to do this. Okay. So what you do now is we'll change variables in our optimization problem. Instead of x, we'll go with z, and you end up with this. And now it's totally unconstrained. Still a convex problem because f is simply applied to an affine transformation here. By the way, if the original f was self-concordant, it still is, right? So that's it, and we know how to do that. I mean, we can apply Newton's method, gradient, steepest descent, whatever you like. Okay, so that's the idea. Okay, and if you want, after solving this problem, you can reconstruct x. I mean, that's x, but you can also reconstruct the optimal Lagrange multiplier, and it's got just a particular formula like that. That's if you wanted it in the original one. Okay, so, I should mention something about the interpretation. Sometimes it's useful. Sometimes you want to know this, because the interpretation of nu star is actually something like, it's something like the prices for if every row of this is interpreted as some kind of clearing constraint, right? That sort of the amount produced balances the amount consumed or something like that. So that would be the economic interpretation. Then in fact, nu is a vector of the optimal prices of each of those commodities. It said, basically, as you know, the interpretation of nu star is, you know what? What if you allowed me to change B a little bit? What would happen? Nu star tells you how the optimal value would change. Okay, so I mean, I just mentioned this. Okay, so that's that. So what this kind of says is at this point, you don't need to know any more, and from some point of view, you don't need to know any theory about equality constrained problems because you just reduce it to an unconstrained problem, it's done. Okay, so quick example of that. Let's solve, here's an optimal allocation with a resource constraint. So I minimize a bunch of individual costs subject to all these things add up to B, right? And so this is an allocation problem, right? B is sort of an amount of resource I have, and I'm dividing it up among a bunch of agents, right? N agents, and I want to do that. Sometimes this is called the social cost in that context, right? And here, by the way, the optimal Lagrange multiplier, which is scalar, actually tells you the optimal price for the commodity that we are allocating. Okay, so just, I mean, it's kind of obvious, but okay. So that's a constrained problem. How would you solve it? Well, what we can do is just this. We'll do the following obvious elimination. I could take x hat to be ben. Here's another x hat, right? It's b over n times the vector of 1s, right? That's a uniform allocation, but it doesn't matter. So I'll take it to be ben. That means I give everything to agent n. Okay, and here's a matrix whose range is exactly the null space of A. A is the vector. It is the row vector 1, 1, 1, 1, 1, and the null space of that is all things which sum to 0, right? So that's this. And look, it just says that this transforms to that, and that's unconstrained. By the way, so that says whatever you can say about this problem, you can solve it super fast. Okay? Actually, we'll get to that because we're going to see that there's a way to get the structure, to exploit the structure directly. Newton's step for a equality constrained problem, and it looks like this. It says you form this 2 by 2 matrix, right? 2 by 2 block matrix here. You have V and W, and you solve, and on the right-hand side you have the gradient and 0, right? And look, if you read the first one, this says AV equals 0. That means V's in the null space. If you're in the null space, by the way, that says that you can freely add it to a feasible point X, because if AX equals B and AV equals 0, I can add any multiple of V to X, and it still satisfies AX plus, HV equals B, right? So that's the second. And the top one basically tells you something. It actually has to do with that dual residual, which we'll talk about in a minute. So a couple of interpretations of this. Notice that it reverts to the Newton step when there are no equality constraints. Because when it's no equality constraints, that's just a 1 by 1, and it's Hessian times V equals minus gradient. That gives you the Newton step. So where does this come from? Lots of interpretations. Here's one. Form the quadratic approximation of f at x. That's this thing here. And notice v is like a step or a perturbation. Okay? Then, the equality constraints are their equality constraints. You don't need to approximate anything. You don't need to linearize. Or you could even, right? You could implement a method, which is the linearized method, and you would call it on an affine function, and it would simply return itself. Right? So this would be just fine. And so how do you linearize the equality constraints? They're just the same. Okay? Now, this we know how to do, right? Because this is minimizing a convex quadratic in V subject to equality constraints. We know how to do that. And guess what? All you do is you solve this equation here, and that gives you V and W. So that's another way to say it. And notice that preserves the spirit of Newton's method for without equality constraints. I mean, so instead of being explicit, you should say Newton's method, really, the idea behind it is this, is you implement a method that says, get quadratic approximation or something like that. And so then you call it you do f dot quad approx at x, and it returns a quadratic model valid near that point. And then you minimize it. That's Newton's method, right? This is the same thing. It says you call the same method on f, and now you minimize it, but subject to the equality constraints. But we know how to minimize quadratics subject to equality constraints because that's linear algebra. Okay, so that I think it's natural. Another way to say it is this. Here's what you really want. What you really want is when you take a step here, you would like this thing to be 0. That's what you'd like, right? That's what you really want. That's driving our d, the dual residual, to 0. And so what we do is we simply take an approximation of this. That's in general non-affine. If f is quadratic, it's affine. But if f is non-quadratic, that's affine. And an approximation of the gradient at x plus v is very simple. It's the gradient at x plus the Hessian, which is, after all, the derivative of the gradient, multiplied by the step. And if you solve these two equations, that's this. Okay? So you can either call the linearized method on the optimality conditions and solve the linear equations. You can solve you can call the quadratic method on the original problem and then solve that, right? Either way, and they're the same thing. Okay. So the Newton decrement it can be written several ways. This is one of them, and it's that. By the way, there are some other formulas for the Newton decrement which are completely false in the equality constraint case. One is, I think, delta x Newton transpose times the inverse of this times that, right? One of the formulas looks like that, and it's wrong. Okay, but so you have to be careful. A couple of the formulas for Newton decrement are correct. Others are wrong. Okay, and it's the same thing. It simply gives you an estimate. It's the difference between. It says that if you form the quadratic model, solve the constraint problem, how much would the objective go down? And that's lambda squared over 2 is what that is. So it makes perfect sense. It's also the directional derivative in the Newton direction, so that also is preserved. But it is not equal to that. That's an example of one of the formulas that's just wrong for equality constraint. Okay. Now, here's Newton's method with equality constraints. So here's the algorithm. You compute the Newton step and the decrement. You quit if the decrement squared over 2, which is your expected decrease, is less than epsilon. Then you do a line search and you update. So guess what? That algorithm is identical to Newton's method for unconstrained. It's exactly the same. The difference is we have now kind of overloaded a few things here. Newton step has been overloaded to handle equality constraints. It doesn't mean Hessian inverse minus Hessian inverse gradient. It means solve this big KKT system, right? And we also overloaded the Newton decrement to mean something appropriate in that case. Okay, otherwise it's identical, the algorithm. And it's a feasible descent method, meaning every step x is feasible and your objective goes down unless you're at the optimum point. And it's affine invariant. If you change coordinates, it doesn't matter. Okay? I mean, you get a commutative diagram. You get exactly the same algorithm. Okay. By the way, what that means is that scaling is sort of a second order issue for Newton methods, right? Meaning, yeah, if you scale things by 10 to the 38 and 10 to the minus 38, you're going to have underflow and overflow and numerical issues and things like that, sure, okay? But you can scale things very happily by 1,000, 10,000, and it will work fine. And the reason for that is, to a numerical analyst, a condition number of a system of linear equations of 10 to the 3 or 10 to the 4 is not that big a deal, right? Whereas for any first order method, condition number is a first order effect. If the condition number is like 10, it's going to work super well. If it's 100,000, just forget it. For all practical purposes, it doesn't work. If it's 1,000, it may not work. Okay? So that's the idea. Another way to say it is, if your method is working with a gradient method, I can break it by scaling. Scaling even by modest scaling. Newton's method, I won't break. It'll work perfectly. Okay? So, okay. Now, it turns out there's a we don't have to do any analysis of this. And the reason is the following. There's a commutative, you get a perfect commutative diagram here. If you take a problem, you take an original problem with equality constraints, then you eliminate the variables. You do variable elimination. Then you apply Newton's method. You get a commutative diagram with applying Newton's method with equality constraints. It's identical. And that means we don't have to do any analysis at all because we already know it all. We know everything, including for self-concordance, I might add. We know everything. Nothing to do. So you don't need any convergence analysis. That's good. Now we're going to talk about something that's different. And honestly, this is maybe the more useful one, and this is actually the more modern one. And it's actually probably more useful. So here it is. It's the idea of a Newton step at an infeasible point. And so the basic idea is that you really say that what you want to do is you write down the residual, right? And that's in Rn plus p. And it's the following. It's the dual residual and then the primal residual. And what you want to solve is a set of nonlinear equations in n plus p variables, right? And the number of equations you have is n plus p. Okay? So that's what you want to do. So that's one view of it. Now, by the way, solving nonlinear equations in Rn plus p with n plus p equations, it's super complicated. Like, you don't even know that there exists a solution, right? I mean, here you know there's a solution because, well, it's a convex problem and so on and so forth. So that's the nice part, is that there's some regularity to this. But Newton's method simply says, I want to solve that equation. Here's what we're going to do. Y is going to be actually a primal dual variable. It's going to be a pair consisting of a primal variable and a dual variable. And what we're going to do is this. I want R of y is 0, so I'll imagine that I'm going to go y plus delta y. That's going to be my step. And what I would like is I want that to be 0. But that's equal to R. I mean, the linear approximation of R is affine, but people call it linear, is R of y plus dr, that's the derivative, or Jacobian, multiplied by delta y. Dr is exactly that. Now, you get a similar set of equations. Here's what you get. You get this. Actually, the right-hand side is a little bit different here. Actually, it turns out these are completely the same, right? If here we're actually calculating that's the full Newton thing, the full dual variable, and here we're calculating an update to a dual variable, okay? So this is a very nice form of Newton's method, and it is to be interpreted this way. It says, and you should think of it as a primal dual method, because every step you're updating a primal and a dual variable, right? And the idea is to drive both the primal and dual residuals to 0. And so you solve this. It's the same KKT system, and on the right-hand side are the residuals of both, right? So, by the way, it generalizes the Newton step for a feasible point, because if x is feasible, that's 0. And guess what? You get the Newton step that we had before for feasible points. So it's a generalization. But you have to be kind of careful. Let me tell you why you have to kind of be careful. What's kind of cool about this is this defines a Newton step even when you're infeasible. Notice you don't satisfy ax equals b. It says there's a direction to go in. Now you have to be very careful because that direction to go in is a combination of two things. There's one is you want to make f small. So you're going to kind of be going in the direction minus gradient f. I mean, that is, after all, what we're trying to do. But if you don't satisfy ax equals b, you're also going to be going in a direction towards which ax equals b, right? So you're going to have kind of these two directions. And you also have to be very careful because in a problem like this, you could end up, it's not a descent method. I mean, for obvious reasons, right? If that's my equality constraint, right? And here's my function I'm minimizing, right? You know, I don't know, maybe the solution would be right there. It's whenever the tangent touches this line. That's the solution, right? Now, suppose I started right here. That's my initial point. Okay, so at that point, what's the gradient of f? It's 0, right? So the only minor problem is you're not feasible, right? So the Newton step, in this case, is going to point you to somewhere on the line here, right? Because if you take a full Newton step, the equality constraint becomes feasible. Okay, so that's the idea. And by the way, what will happen to f from your first iteration? It'll go up. Has to go up because you started at the minimum of f, right? So it's clearly not a descent method. Now, when you see f go up, someone says, hey, that's a crappy job you did on that optimization. I gave you an initial point, and the first thing you do is your function value goes up. And what do you say to that? What would be what's your comeback? Yeah, it's like, well, dude, your point wasn't feasible. So it had excellent objective, but it didn't satisfy the constraints. So that's all. Okay. I just mentioned this because things like this come up and you'd be surprised, actually. So, okay. So it says the line search is different. So you don't measure progress by the function value, obviously. Although you should measure two things: the primal and dual residual norms, or some people lump them together into one. And either way. By the way, this will tell you something if you look at things like Sedumi or SDPT3 output. I don't know if you do, but when you run CVX, a few of the columns are now going to be demystified. They'll be fully demystified by next week. But you will see things that say RP and RD. Or it'll be obscure. It'll say D norm and P norm. And these literally mean the primal residual and the dual residual norm. So, okay. Okay, so here it is. What you do is you compute these Newton, the primal and dual Newton steps, and then you do a backtracking line search on the norm of R. Okay, so on the total residual. That's easy enough. And it turns out the directional derivative is simply minus the residual. That's a quick calculation. And so you get a very simple code that looks like this. Then you update x and you keep going. It's not a descent method, but I tell you what does go down is the norm of the residual. So whenever you have an algorithm and people analyze it, there's the basis of a proof or something is there's some function that goes down, right? In the Newton method, the gradient descent, the things, we focused on the function value going down. I mean, what could be more natural? You want to minimize f. So it's kind of cool that the thing you want to happen happens actually locally at every step. Greedily it happens, right? Here, it turns out that by the way, it's got all sorts of names. I think one name, one is a Lyapunov function, and there's another one, I forget, there's all sorts of names in optimization too for that. I forgot the name. And in computer science, they have yet another name, which I also can't remember right now. But anyway, but the concept is very simple. You have an iterative method, and you have a function that goes down every step, and that's the basis of your proof that it works, right? So, by the way, there's a huge practical advantage of having such a function if it's explicit, because it basically says you can do anything you want in that algorithm, any modification you want at all, as long as you make sure that function does go down, right? So, for example, you can insert weird steps in your algorithm that does some kind of weird local optimization, okay? But you better make sure that local optimization better ensure that Lyapunov function goes down. I just remembered one of the names, merit function. That's one of them. But there's like 5 of them. And anyway, the concept is clear. Okay, so here it turns out the merit function is the norm of the residual. So let's talk about solving KKT systems. How do you solve something like that? Well, there's lots of ways. So one is you just use LDL transpose because that's a symmetric indefinite system, right? It's indefinite because you look at the zeros down there. And in fact, it has exactly n. Well, if H is positive definite, it has exactly n. Actually, if it's solvable, it has n positive eigenvalues and exactly m, or p, I think it's p, is the size of the equality constraints, p negative ones. Okay? So that's very simple. You just plug in this stuff and use LDL transpose factorization. You can also do elimination. What you do is, in many applications, H will be diagonal, block diagonal, something simple. There we go. And so H will be, and then H would then be a natural target for elimination. I mean, for sure, if you saw that system and H was diagonal, I'm hoping every single one of you would have an overwhelming urge to eliminate the 1-1 block. You should, and we're going to train you until that's the case. Okay, so that if H, but doesn't, I mean, the math doesn't matter either way. So if you eliminate the V here, you end up with a system that looks like this. By the way, that is the negative Schur complement of that matrix, right? Because the Schur complement is 0 minus A, H inverse A transpose. That's the Schur complement. Well, with a minus sign, okay? So that's a Schur complement. And by the way, I think this is called, people refer to this system as the reduced system. That's standard notation. So people would say, you'd say, oh, what are you doing, Newton, blah, 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 and say, oh, yeah, how are you solving it? And they'd say, reduced system. By the way, They then call this the augmented system. Don't ask me why. It's the KKT system. That's augmented and reduced. Okay? So you could do this. Now, if H is singular, there's lots of interesting things you can do. One is that, in fact, any solution of this is identical to a solution to that. You can just check. But the point is that what this allows you to do is to make sure that this 1-1 block is non-singular, right? Then you can apply elimination. So, okay. Now we're gonna finish with an example, and it's gonna tie a whole bunch of stuff together. And actually, you're gonna see something really interesting, which is to say that there's lots of methods to solve a single problem. They go through duality and stuff like that. And what you'll see but I'll get to the punchline right now. That we're going to look at a problem, and you can solve it many ways. You could solve the problem, you could solve the dual, you could do this and that. And in each case, if you use Newton's method, this is going to be the critical part. If you use Newton's method, the system of equations you're going to come down to solving in each step of each of those is not exactly the same, but it has exactly the same structure. And that structure will be such that if you know what you're doing, you can solve it efficiently, right? And so what's kind of interesting about that is a lot of times you will actually hear people who don't know any better say things like, well, I'm solving the dual, right? And they might say that because it sounds cool, right, to solve it, doesn't it? I mean, people don't know, you say, well, I'm solving the dual. Anyway, sounds sophisticated. And you say, why is that? You go, well, I get efficiency or something. I mean, there are good reasons to solve duals, like you can distribute stuff and parallel. That's another story. But if you're doing like a Newton method, there's absolutely no reason to do it if you know linear algebra. If you know numerical linear algebra, there's absolutely no reason to do that. We'll see that. What is different, actually, are the initializations. So, all right, let's jump into it. We want to calculate the analytic center of AX equals B and X non-negative. And that's the feasible set for a classic linear program, right? Minimize C transpose X, subject to X equals B, X bigger than or equal to 0. That's the feasible set. It's the intersection, if you like, of an affine set with a non-negative ortho. That's what it is. And we want to write down, so the analytic center is this, right? That we want to minimize some of the logs, that's the barrier associated with that, subject to X equals B. Okay? So now the dual of that problem, you can work it out, is this. You maximize this. And here, it turns out this thing is strictly, the original function is strictly convex. And that says that if we solve the dual, we can recover the primal solution. And there's a simple formula, right? It's a really dumb formula for it. It's like, it doesn't even matter what it is. It's there, right? And you can, by solving the dual, you get the primal. Okay. And they're kind of interesting. Let's take a look at them. The dual is unconstrained. Well, not quite. There's an implicit constraint that A transpose nu is positive. Okay, so the domain of the dual is a bit complicated. It's the set of vectors nu for which A transpose nu is positive. That's actually a open polyhedron, right? So the domain of the primal is simple. It's R plus to the n, R plus plus to the n, right? It's all positive vectors, right? Sorry, intersect with AX equals B. My mistake. So, okay. So they're different. Okay, so let's look at some things. Here's what we can do. Let's just take Newton method with equality constraints. So we have a problem with 500 variables, 100 equality constraints. And if you run Newton's method, you get something like this. And what we're doing here is these 4 traces show you just 4 different starting points, right? And that looks very Newtonish. This is what you should see, and you will see, presumably, later this week. They're doing it this week. Okay, so you'll see things that look like this. This is what you're shooting for, right? And the idea is, look, that's a 10 to the 15 range there. So this may be actually quite perfectly good, respectable convergence, but on a plot whose range covers 10 to the 15, you're not seeing it, okay? But the key thing you should see is something like that, right? That's your basic Newton behavior, right? By the way, that should also correspond to the place where you do undamped steps. So the step size should be 1 in that region. Fine. And this is what you expect. Okay. Oh, the initialization was interesting. We needed to know a positive vector with AX equals B, right? If this is just a general problem, you don't know such a thing, so that would be kind of a pain. Let's apply Newton method to the dual problem, okay? So here, if you apply, that means what we do is we need a vector nu 0 that starts in the domain, and we apply Newton's method, and then here it is for 4 different things. And by the way, you might be tempted to say, in fact, I will give you the entire fallacious argument because I promise you will hear this from someone you know, in which case you can correct their misunderstanding. They would say, I have a fantastic method for solving this problem. I'm going to solve the dual. And someone says, well, why would you do that? And they would say the following. Number one, that original problem has 500 variables. The dual has 100. Last time I checked, 100 is smaller than 500. Person says, you're solving a problem with 500 variables. I'm solving one with 100. Okay, that's fewer. That means it's 125 times faster, number one. Number two, to add sort of just a bonus, you're taking 15, 20 steps. Look at this. This thing typically converges in 8 or 9 steps. I'm half the number of steps. My advantage over you is 250x. Plus, you get the added bonus that it sounds cool if you say, I'm solving the dual, because it sounds more sophisticated. You know what I'm saying? Right. Everyone following this argument? Okay. We will see that it is totally and completely wrong. Okay? But that's the argument. You will hear it from people. Okay. Now let's look at another one. Let's look at infeasible start Newton method. Now, this is its huge advantage, and this is probably why this is more useful than a lot of the others, although it depends on the situation. The initialization is very modest. The only thing you need, it does not have to satisfy ax equals b. It only has to be in the domain. The domain is the sum of the logs, right? So does someone want to suggest a starting point? All ones, thank you. All ones. That's an excellent starting point, and you start from there. And then it's actually kind of cool, right? Because the first couple of, steps, you'll see 2 things happening, right? The function may or may not be going down, but you'll be moving towards ax equals b, right? So, okay. And if you do that, here you go. You get between 10 and 20 steps or something. That's the infeasible start method. But the first one that actually puts approximately 0 actual burden on you. You could write this code right now, right? Because it doesn't need some weird thing. Okay. But now let's go back and look at these 3 methods. And if you look at them, here's what's going to come up. It's really quite cool. If you look at the original one, you end up solving this system of equations to determine, to get a Newton step. Okay? And look what it is. It's diagonal A transpose, right? That should induce in you an immediate urge to eliminate the first top delta x block, and you will get the following. You will get A times, you'll get this reduced system times A transpose W equals B, right? So that's what you'll get, and you'll solve that, right? Okay, now if you solve the Newton system for the dual, well, you end up solving something that looks like this, okay? But if you look at that carefully, you realize, it's a totally different system from this, right? But the structure is the same. It's A diagonal A transpose. It's a system of that form. That's the coefficient equation. That's what you have to solve, right? In the third one, the Newton system looks like that. The only thing different here is instead of the dual variable, you now have a delta dual variable, and instead of a 0, you have a residual here. And you get this, so it's the same actually as the first one, and you get the same thing. The right-hand side is different, but that doesn't matter. So in each case, you end up solving A, D, A transpose, W equals H. What that says is the cost of the 3 methods is identical, despite this one appearing to have 100 variables, whereas this one has 500 variables, and this one down here has 600, because you would say, well, I'm updating the primal and the dual, right? So all of this says, don't be fooled by when someone walks up to you and tells you about the complexity of Newton's method. Ask a few questions to probe if they know numerical linear algebra, and if they don't, ignore everything they have to say about what's hard and what's easy, because they're probably completely wrong. Okay, so that's the idea. By the way, I want to finish with just one comment. If A has sparsity, ADA transpose, that comes up all the time. And in fact, you can get the sparsity pattern of ADA transpose, right, which is what you'd have to solve, directly. And in this case, it's going to depend exactly on this. this will have a non-zero in the ij position if and only if A, if you make A if you make a graph out of A, or actually if you take the matrix A, only if there is I guess it's a row, if I and J share a non-zero in that row. That's the condition. So in a lot of practical applications, this would make it very clear what the sparsity pattern is. Okay, so anyway, so the bottom line is that for a lot of these problems, things that would appear to be quite different in complexity, right? Numbers of variables, things like that, actually aren't. But that's assuming you are applying smart linear algebra, right? If you just made these and did backslash on each one and they weren't sparse, it would come up with the same conclusion you'd want. This would be way better because it's 100 variables, way better than that, and that's better than that. All right, the next example is network flow optimization. So the idea is this. We have a network. We have flows. So xi is the flow along arc or edge I here. Phi I is a cost function for flow along that arc. And AX equals B. I'll say what A is. A is the node incidence matrix. So the node incidence matrix is the following. It tells you whether there is, looks like this, right? So you start with this, and you put a +1 and a -1 in each. So each of these are the nodes here, and these are the arcs. And you put a +1 and -1 in each column to tell you which way that arc, where it goes from and where it goes to, where its head and tail is incident. And then this matrix here is rank deficient. Well, for example, if you have 1 transpose on the left times this matrix, you get 0. That would actually be perfectly okay to leave it here, but instead it's conventional to simply remove 1 row, and that gives you a reduced node incidence matrix, A tilde, and if the graph is otherwise connected, then that matrix is not rank deficient. That's standard. We could say lots of things about that, but this is the same. This is done in electrical engineering. This means you choose 1 node as the ground reference or datum node. Okay, so that's all that matters there. And AX equals B is flow conservation. So that says that if at every point, or at every node here, if I have some arcs flowing in and some arcs going out like this, it says, for example, if that's x3, that's x5, that's x10, and that's x12, that says the following, that x3 plus x5, that's flowing in, that has to equal x10 plus x12. That's the outflow. So basically, AX equals B is flow conservation. And I should say what B is. If B on the right-hand side over here, the right-hand side of this equation, that is an external source or sink. So that looks like that, right? So if there is nothing else connected to that node, then the associated B sub I is 0. Otherwise, that's a source or sink, right? So, okay. So this says, among all flows, please find the one that minimizes the cost. That's the cost. Okay. So we're going to take a look at that, and we're going to figure out how to solve this problem. More interestingly, we'll see how structure comes in. Well, the KKT matrix looks like this. We minimize a sum of functions of the individual variables. But I know what the Hessian of such a thing looks like. The Hessian is the diagonal of the second derivatives, right? So the Hessian is here. It's diagonal. Looks like that, and that's up here. Then I put A over here because I have AX equals B as the constraint. This is my Newton, my KKT system involves A and A transpose here, like that. And I have to solve that equation. And you're staring at it, you see a diagonal matrix here, and by now you should have a very strong urge to eliminate that block, right? And if you do eliminate that block, you're going to get this thing. That is the negative Schur complement of this matrix with respect to H. So you get this thing. Now, by the way, H inverse shouldn't scare you, even though if H is big, because H is diagonal. So That was the whole point after all. It's easy to invert. So you end up solving a system that looks like that, okay? But we can actually say more, because this is A times H inverse, that's diagonal, times A transpose. And the sparsity pattern, well, it's the same as the sparsity pattern of A transpose. Now A is here, a fat matrix like this. So A transpose is the small one. A diagonal one doesn't affect the sparsity pattern, okay? And this is nodes here, right? So this is a nodes by nodes matrix, and we can say exactly what its sparsity pattern is, okay? This sparsity pattern is the following. An entry is non-zero here if and only if nodes I and j are connected by an arc, okay? So that suggests, well, it depends on the network, of course, right? So that suggests something like this. Well, I don't know, I can ask you a question about it. This says that if the degree, right, if each node has a maximum degree d, say, that's the number of connected edges, then that tells you that every row of this matrix, and column, by the way, has a maximum number of 3 entries, non-zero entries in it, right? And that tells you that this matrix is probably sparse too, and that suggests that you could do a sparse Cholesky on this matrix, right? And in fact, if the graph is sparse enough, and if the gods who control the heuristics used to order Cholesky factorizations for sparse matrices are smiling on you, then there will be very little, if you're lucky, there'll be not much fill-in, and that says basically that you can solve this system and do 1 Newton step in something that's not much more time than the number of flows, or so n, so of n. And you can, if you're lucky, you can solve a pretty big flow system pretty quickly, and Newton steps would only cost you something that's really kind of on the, I mean, it's going to have a not totally small multiplier in front, but it's going to be something that would have not many, it wouldn't be much more than just walking over the graph once. So, and this would allow you to solve this very, very fast. Again, that requires the sparsity here.